Okay, general relativity step by step. Last time I set up this rather peculiar coordinate system here with Cartesian and rather a peculiar system indexed by the horizontal distance that you move and the angle here. So you've got this quite nice relationship between the two. So what I'm going to do is to define the forward Jacobian as the matrix of dh, dx, dh, dy, d theta dx, d theta dy, and of course on the right hand side I'll do the backward relationship equals. So let's do it. Get rid of those brackets, they don't help anything. Equals. Right, dh dx is just 1, of course. Dh dy is 0 because there's no y here. So what that means is that as y changes, which is moving up and down this blue line here, we don't change the y value. Sorry, as y changes, as we move up and down here, we don't change the h value at all. The h value stays the same. So that means that that's a 0. These things can get quite confusing. That's why one of the reasons why I've used the coloured system here. Theta equals arctan y over x. Let's have a look at that. We need d theta dx, which is, so that's yx to the minus 1, so it's minus yx minus 2. And I'm sure you know that the differential of arctan is 1 over 1 plus x squared. X squared. Just move that over to the right a little bit. And then we need d theta dy from this formula here, so that's going to be plus x minus 1, 1 plus y squared over x squared. And I'll do a little tiny bit of tidying. Multiply top multiply by x squared, so it's minus y over x squared plus y squared plus x over x squared plus y squared. Now, the backward way is this one. Let's get it right, x by di h, di x, di theta, di y, di h, di y, di theta. It's always worth writing it out. Equals. Now then, to do this one, what we need, the relationship we need is x equals h, and because we need dy by something, we've got y equals h tan theta. So let's just put those together. Di x, di h is just 1, of course. Di x, di theta, there's no theta here, so that's just a 0. Di y, di h is tan theta. And di y, di theta is h. Differential of tan is sec squared theta, which is that there. Okay, let's just translate that. Now you see, what I want to do, of course, is to multiply this matrix by this matrix here, but I can't, well, I can do it, but it's in an unhelpful form because this one has got h's and thetas and this one has got x's and y's. So I need them both to be in the same format. I'm going to rewrite that as 1, 0, tan theta, and then h sec squared is 1 plus tan squared. So I'm going to write this out here as 1 and 0, of course. Tan theta is just x over y. And then h times 1 plus tan squared is just x, because x equals h, times 1 plus y squared over x squared. Oops, I'm sorry, that's y over x. And I'm going to tidy that up a little bit even more. I'm just going to multiply that matrix. Actually, I'm not. I'm just going to leave it. So the product, j, which way around have I done it? This one here is the forward transformation. So jf, matrix multiplication with jb equals a, b, c, d, and it's a better equal the identity matrix. Because if it's not, I've made a mistake. A equals, so we need top left, so it's the top row with the left column. That 0 means that we've just got 1. B equals 1 times 0 and 0 times something is 0. C equals, that's not quite so obvious, is it? It's minus y over x squared plus y squared plus y over x times x over x squared plus y squared. What am I doing here? This C is the lower left one, so it's the low row with the left column. and we've got minus y over that from this one times that one, and we've got x over x plus y times y over x equals, of course the x is cancelled, 0. And d equals, oops, d equals what? D equals x over x squared plus y squared for this term here times x times 1 plus y squared over x squared. One of the things I want you to observe is how difficult this is. The algebra is quite hard and quite challenging. It's not super difficult or anything, but what have we got here? We've got an x squared on the top times that, so it's x squared plus y squared over x squared plus y squared equals 1. Fantastic. So JF matrix multiplication JB equals this ABCD 1 0 0 1 QED. And we'll come back to that result again and again and again in relativity. I'm going to stop there.